welcome to Chapter 9 of Year 1 of the Applied Mathematics course. In this chapter we look at constant acceleration. Okay, so there's 4 different things we look at. First of all, I look at displacement time graphs, which is this video. We then go on to velocity time graphs. We then derive the formulas for constant acceleration, and then we use those formulas to solve various types of problem. Okay, before we go on, you might want to have a go at the prior knowledge check questions at the start of the chapter. Okay, first of all, I want to have a look at the difference between distance and displacement. Okay, we've got a runner here, and this is our start point. So starting from here. So our runner is going to run all the way to the end of this scale here, which is 200 meters, and then he's going to run back to this point here, which is 100 meters away from the start. So first of all, the total distance, which we normally use D for, is how far that object has traveled, how far the person has traveled. So he's gone 200 meters out plus the 100 meters back. So the total distance is 300 meters. Okay, that is different to displacement. So displacement, which we use the letter S for in mechanics, is the position of the object relative to the start. So this person here is now 100 meters away from the start. So his displacement at this point in time is 100 meters. Okay, so we've got 2 formulas, average speed formula and average velocity. Average speed uses a total distance divided by time, and this is what you would have looked at GCSE. So in this particular case, the average speed of this person is the total distance. The total distance he's travelled is 300 meters. Total time he's travelled is 60 seconds. So his average speed is equal to 300 divided by 60, which would be 5 meters per second. Okay, we don't normally write it like that. That looks a little bit messy, so you might have seen this before, 5 meters / second. However, in mechanics, we use this terminology, 5 meters s to the -1. The s to the -1 comes from this because s is on the bottom of the fraction, that is to the power of -1. Okay, now the average velocity is different to that. The average velocity uses displacement, so it's the total displacement divided by the time. So the displacement of this person at the time we're looking at is 100 meters. The time he took was 60 seconds. So therefore his displacement is 10 over 6, 5 over 3, which is 1.6 recurring, 1.67 to 3 significant figures. And again, it's meters per second, so -1. Make sure you're writing your significant figures. Okay. So that's the difference between distance and displacement and speed and velocity. Okay, speed uses distance, velocity uses displacement. Okay, moving on to the shape of various types of graph. Okay, we've got 3 graphs here, and I've got 2 extras which I'm going to draw for you. Right, in this graph, we've got S, the displacement on the y-axis, and T, time, on the x-axis. And we can see this line here represents a journey, and this journey has not changed the displacement. The distance from the start has not changed, therefore this object here is stationary. Okay. In this second graph, we can see the displacement is increasing over time, and because it's a straight line, it's increasing at a constant rate. So we call this constant velocity. Whereas in this third graph, you see it's a curved line. So to start off with, it's quite a shallow line, so it's increasing at a slow rate, and then by the end, the distance at the displacement is increasing at a very fast rate. So that's an increasing velocity, which we know as acceleration. What is accelerating? Okay, so if it's a straight line, it's a constant velocity, straight diagonal line, a constant velocity, straight curved line going upwards, it means it's accelerating. Okay, a couple of other things which are not in the textbook but are very important. Notice this has got a positive gradient. Now, the gradient of the line, basically what we're saying here is the gradient of the line gives the velocity at that instant. So at this instant, any instant here, it's a flat line, so it's got no velocity. The gradient is 0, the velocity is 0. Here, the gradient is the same, so it's got a constant velocity and it's positive because it's a positive gradient. Here, the gradient is low to start off with and it's increasing at the end, so the gradient is increasing, therefore it's increasing velocity, acceleration. What would happen if the line was going in this direction? Well, let's think about what's actually happening. The distance, the displacement, or the distance that the object is from the start point is decreasing. So in this particular scenario, it's getting closer, therefore the velocity is negative. Okay, so here will be a negative velocity. Getting closer. You can have negative velocity, whereas speed you would never have negative. Whereas, okay, so here's another scenario. So in this scenario, I've got a curved graph that's going the other way to the graph up here. So in this scenario, the gradient is steep to start off with, but it's getting more shallow. So the gradient is decreasing. So velocity is decreasing. And we call this deceleration. Okay. The other way that you can talk about that is negative acceleration, which would be the same as the deceleration. Okay, moving on to the example. Okay, we've got a cyclist who rides in a straight line for 20 minutes. She waits for half an hour and then returns to the same point, but in 15 minutes. Here's the graph. Work out the average velocity for each stage of the journey. Okay, so I'm going to name each stage of the journey. Let's go X, Y, Z. So we want the average velocity for each stage. So for the velocity, let's use V. For X, the velocity in the first stage is equal to, so remember, it's the displacement divided by the time. Displacement S divided by the time T. So the displacement in this first part of the journey is 5. Okay, so it's got from 0 to 5. The time it's taken is 20 minutes. Now, this wants it in kilometers per hour. So 20 minutes is equal to 1/3 of an hour. So we can do 5 divided by 1/3. You can work that in your head, or you can do it on your calculator, and that will give us 15, and it's kilometers per hour, h to the minus 1. Okay, so that's for stage X. Velocity at Y. Now you can probably pretty much tell straight away from looking at the graph the distance has not changed, but let's put it into the formula. So it's 0 over how long has he been doing it for? Half an hour, 30 minutes, half an hour, divided by half. 0 divided by half is going to be 0 kilometers per hour. It is stationary. And then the final one, velocity at Z is equal to, so this time it's travelled backwards, it's back towards the start point, so it's a negative displacement. So it's travelled negative 5 kilometres, and that's important because the displacement is always relative to the start point, and it's taken 15 minutes, so that's a quarter of an hour. So negative 5 divided by 1/4 is equal to negative 20 kilometers an hour. Okay, so that's for part A. There's the various velocities at each stage of the journey. Part B, write down the average velocity for the whole of the journey. So the average velocity is equal to the total displacement. So from the start to the finish. So at the finish, the displacement is actually 0 because it's at the starting point divided by whatever it is, 65 minutes. So the average velocity is 0 kilometers per hour. Okay. Whereas part C is different. It's asking for the average speed. So the average speed is equal to the total distance. So the total distance you travelled 5 out, 5 back. So in total, he's travelled 10 kilometres in a time of 65 minutes. Now remember, we've got to have that in terms of hours. So we can work out what that is by doing 65 divided by 60 in terms of hours, or you could use the time button on your calculator. And if we do that into our calculators, it will give us 9.23 kilometers per hour. Okay, that's all the examples in this first part. You can now have a go at exercise 9A.